In this video we are going to discuss chapter 10 of the textbook written by C.D. Walls. The title of the text is Geometry of Numbers. It's also interesting note that it's the most important theorem in unit in that chapter in the 10th chapter. The statement of the theorem is if theta is irrational and if alpha is any non-integer real number, if theta is any rational is an irrational number, if theta is an irrational number, and if alpha is any non-integer real number such that x minus theta y minus alpha equal to 0, such that it satisfies the condition that x minus theta y theta y minus alpha equal to 0 has no integer solutions. It has no integer solution means x and y has no integer values satisfying the given equation x minus theta y minus alpha equal to 0. Then for any given positive number alpha greater than 0, for any given positive number alpha greater than 0, there are infinitely many pairs p and q where p and q are integers, such that modulus of q into p minus theta q minus alpha is less than 1 by 4, and modulus of p minus theta q minus alpha is less than epsilon. Here epsilon is a positive quantity, given positive quantity, and that has the property that it is very close to the number 0. So the two inequalities are satisfied, and the two inequalities are modulus of q into p minus theta q minus alpha is less than 1 by 4, and modulus of p minus theta q minus alpha is less than epsilon. The proof is due to Blish fields, and the proof is completely given in chapter 10. To develop the proof, to develop the steps of the proof, we introduce a third variable z and make the non-homogeneous equation homogeneous. See here, before to begin the proof, we are going to consider a prism. The boundaries of the prism are given by the set of equations which you can those equations you can see here. These are the equations 10.a 10a. The equations are given in 10a, and a prism has 6 sides, 6 faces. Two of these faces are given by modulus of z is equal to 2, and other 4 faces are given by modulus of x minus theta y minus alpha z plus modulus of t times modulus of y equal to root t. But here we want to see what the value t is, what's the meaning of t, and how these equations are written. All those things we want to see. But the main important thing is that we are going to consider a prism. Prism is a three-dimensional object, see, t is a parameter. Here it is mentioned that t is a parameter, and z is a third variable that we bring in. But but where are the other two variables? How do we get the other two variables, x and y? See the equation here. You can see yes, see this equation. You can see x and y are already used. See, in the equation which is given in the statement of the proof, the variables x and y are used. In addition to that, in order to complete the or in order to develop the steps of the proof, we introduce the variable z, and also we use a parameter t. Okay, and these two okay, the two variables and these two newly introduced quantities, the variable, the third variable z, and the parameter t, are used to write the equation of the prism. In the three-dimensional Euclidean space, we consider the prism here. K is used, k over kappa. This letter k is used. Let's call this k. K of t, kt, is used to represent that prism, having the boundaries which are given here. We are going to, in the next in the coming part of the discussion, we are going to see all the sides, the equations of all its sides, all the sides of the prism, and we will explain how those equations are obtained. Here in these two equations, modulus of the numbers are used. You can see here in the first equation there are two moduluses used. In the second equation, one modulus is used. You know that modulus, when we write modulus of a number x, modulus of x, then we have to consider two situations. X can be minus x. Actually, then when we think about the value of that quantity, actual value of that quantity, see, when we write modulus of x, so for let's consider it as a number. When we write modulus of k, if we write modulus of k, then actual value of k can be either negative or positive. See, then it can be thus we have two cases depending upon the sign of the number k. The same is the case with any quantity. So if we consider modulus of x, then we have to think about when of the situation when x is negative, as well as the situation when x is positive. Thus we have the two cases. Okay. In the same way, when we since we write modulus of the first term, since we write, then in effect, you have to consider negative of this number and also the positive of the number. Thus we get two situations here. And due to modulus of y present in the second term, there also you have to consider the negative aspect and also the positive aspect, or the negative situation and the positive situation of y. Thus, in total, how many situations will be there? Now, here we have two options. This quantity is, the inner quantity is negative and the inner quantity is positive. And also here we have two situations. Y is negative and y is positive. Thus, we have two situations here and two situations in connection with the second term. And so when we think about the totality, then we have to see that there exist four situations. So four different cases there exist. How do we get these four situations? Here we consider positive of positive, and here also we consider positive, then plus positive. When we consider negative of this term, and when we consider positive of this term, of the second term, we get the negative and positive. and when we take the positive of the first term and negative of the second term, we get positive and negative, and finally we have the case both negative, first and second terms both negative, then we get negative negative, that is the fourth situation. Thus we can write, considering these four situations, we can write four equations from the first equation, or using the first equation. And the same way, when we consider the second equation, that is modulus of z equal to 2 here, you get z equal to 2, the first equation, the second equation minus z equal to 2. Thus we get two more equations. So these are the six different phases, the six phases that belong to the prism. The above two expressions represent the six sides of the prism, and in the expanded form you can see what I have explained. You can see it. It is written here. So this is writing the first equation here is written by considering both positive. Here we consider negative and then positive case. Here we consider positive and negative case, and here and the fourth case we consider both negative and negative case, and thus we get four equations. Plus, in addition to that, we get z equal to 2 and minus z equal to 2. And thus these six equations, actually these equations determine the boundaries or the sides or the faces of the prism, and that will be more clear when we have a figure to represent all these sides. So that we are going to see in the next figure. We have a figure here, and we have to see that figure. Okay, we are coming to that. Now after simplification, then we get, these equations are then taken to simplify, and after simplification, how do we simplify this? There is only one x term, so but there are two y terms, so that can be combined, and there is only one z term, and that way you can simplify all those, and okay, and then you get this simplified form of the equations, and that are written in 10c in the set of equations 10.c. Okay, and here we have the plane. This equation represents the plane 1, and this one, the second equation, represents plane 2. Third equation represents plane 3, and fourth equation represents plane 4. And the other two planes that can be called the base and the top of the prism can be represented by the two equations of the two planes, z minus 2 equal to 0 and z plus 2 equal to 0. We can take the parameter t. We can take the parameter t such that this parameter, it's a new quantity that's taken in our discussion, and this parameter can be, we have to decide the value of that parameter using the inequality, using this condition, that's root t is less than minimum value of epsilon, minimum value of three quantities, and those three quantities are, one is epsilon, the other is alpha minus alpha in square bracket, and the third quantity is 1 minus alpha plus alpha in square bracket. See, these are the three quantities, and of these three quantities the minimum value is chosen, and root of t must be then less than that minimum quantity. Clearly alpha minus but we know that alpha minus alpha, this alpha in square bracket will be then less than 1. it is less than 1 clearly. That comes from the definition of alpha in square bracket. You know the meaning of alpha in square bracket. So when from the number alpha, if we subtract the number alpha in square bracket, then we get that quantity which is less than 1. If alpha minus alpha in square bracket is between, then we have, there exists two situations. We have to consider two situations. What are those two situations? If alpha minus alpha in square bracket is between 1 by 2 and 1, and when the value is between 0 and 1, in general this quantity, value of this quantity is in between 0 and 1. 0 and 1, okay, but depending upon the when we consider, or by considering 1 by 2 as the midpoint of that range, middle value of the range, then we have the two situations. Alpha minus alpha in square bracket is in between 1 by 2 and 1. That's one case. And then 1 minus alpha minus 1 minus alpha minus 1 minus alpha plus alpha square bracket. 1 minus alpha plus alpha in square bracket is between 0 and 1 by 2 in that case. And okay, but the other situation is 0 less than 0 is less than alpha minus alpha in square bracket, the number alpha minus alpha in square bracket is in between 0 and 1 by 2, or less than 1 by 2 and greater than 0. And that situation, about that situation we are not going to discuss, because but we in this situation we want here we have root 2 is then root 2 is then clearly less than 1 by 2. Why? It's because this is in between. In that situation also we can think about that value of root 2. But in the first case, 1 minus alpha plus alpha in square bracket is in between 0 and 1 by 2, and then we get that root 2 is clearly less than 1 by 2. It's because one of the quantities is a quantity less than 1 by 2, so we get that root 2 less than 1 by 2. But in that situation, the remaining situation, if alpha minus alpha in square bracket is less than 1 by 2, then also we get that since this quantity is less than 1 by 2, then also we get that root t is less than 1 by 2 because we take the minimum. Okay, as a result we can say that always root t is less than 1 by 2. The value of root t is, we can say that root t is root of t is clearly less than 1 by 2. So that's why we discussed the two situations separately. And our aim is to show that the value of root t is less than 1 by 2. Then we have the figure. You can see that figure. This is the picture of okay, for getting clear. A full picture completely, for getting that figure completely in the screen, I reduce the size. Okay, and this is that prism. You can see the prism here, KT, and that prism has its phases. That prism, the bottom for the prism, this is the, you can see the orange colored rectangle. You can see or the parallelogram, you can call that more correctly, we can say that it is parallelogram. See this orange colored one, okay, and that the orange colored, here you can see this is the x-axis. You can see that this x-axis and it is y-axis. See, it should be viewed mounted over x or the xy axis in such a way that it is it's mounted over that xy plane, on the xy plane, not half of that the prism, the middle portion, or a cross section. The cross section of the prism, you can see that cross section colored or boundary drawn using some the color blue, using blue color. You can see the boundary is drawn, and this is that boundary, and this boundary is on the xy plane, and so you can here also you can see that an orange colored parallelogram, also and a red colored parallelogram. You can see an orange colored parallelogram and a red colored parallelogram. This orange colored parallelogram is the base, is the bottom of the prism, and the red colored parallelogram is on the top of the prism. You should you should look you should view this prism in that way. Okay, and this is the top portion, and this is the bottom portion. The orange colored is the bottom portion, and the middle portion, is the blue colored. So the orange colored orange colored side has equation z. That equation is z equal to -2 actually. This is the equation for the lower the base, the bottom. For the bottom of the prism, the equation is z plus 2 equal to 0, and for the top of the prism, it is z minus 2 equal to 0. Z minus 2 equal to 0. Okay, this is the top. The top is the red colored. Okay, that's z minus 2 equal to 0, and the other four sides you can see, and this is one side, and its opposite side is this one, is the opposite side, and you have one more one the side, you can see this is another side, and its opposite side. This is its opposite side. That opposite sides will have some similar equation, but with a slight change. The opposite sides will have similar equations, but changes are also there. Difference is also there. When we compare the two opposite side equations of the opposite sides, then we can see definitely how you can see some difference. Okay, then two of these equations form opposite sides. Pairs of these you can pair these equations to obtain the opposite equations of the opposite sides. Then what are those pairs? See, x plus t minus theta into y. That has a pair x plus t minus theta into y, but this is minus alpha z, that's also minus alpha z, but you can see minus root t is minus root t and plus root t are the differences. So when we compare the first equation, and see, this is the first equation. This is the first equation, and the plane 1 and then plane 4. The equation for the plane 4, that is x plus t minus theta into y minus alpha z plus root t equal to 0. You can see when these two equations, when you compare the first and the last, so the fourth equation, you can see that the difference is only in the sign of root t. And similarly, you can compare the second and the third equation. In the set of equations, you can see they also show a difference in the sign of root t. But otherwise all the remaining terms are same. So these two pairs. First pair is first equation and the fourth equation. The second pair is the second equation and the third equation. And these two pairs make the opposite sides of the prism. Two opposite sides of the prism. Okay, and then equation in 10C represent six planes in R3, and they can be suitably paired to obtain the parallel planes. Yeah, I have explained that how we can pair these equations to obtain the sides. And okay, see that theta y and alpha minus, okay, yeah, that's correct, and minus alpha is and this difference, yeah, the equation, the set 10 dot c, 10 point c and 10 point e make the parallel planes. Okay, examples of, okay, these parallel planes are written here, are explained here. It's an example of parallel plane, and the distance, this one 10 point c given, the equations given here is an example of a parallel plane, and the distance between these two parallel planes is obtained by subtracting okay, one equation from the other. Okay, how can we obtain the distance between these parallel planes? That's a question. You can ask this question. Now, that's an interesting one. Here you see, we have to, if we have two parallel planes, then there will be a distance, perpendicular distance between those two parallel planes. How can we obtain this parallel distance between the parallel planes? It's very, answer is very simple. If we subtract one equation of one plane from the equation of the other plane, naturally, normally we must get the what's that? Yeah, the difference, or the distance between what the quantity that we get must represent the distance between the two parallel planes. So applying that procedure, you can see that the distance between the two opposite planes are root of 2 times root t. So the distance between them are 2 times root t. Then you can, by subtraction method, by subtracting, you can see that, yeah, it is 2 times root t. By subtracting one equation from the other, equation of one parallel plane is subtracted from the other to obtain. In some case you will get negative, minus, but we are talking about the distance, so sign doesn't matter here. So you can avoid that. You can take the modulus of that quantity, and so it is 2 times root t units. Okay, and similarly you can obtain the distance between the other two planes. That also can give you the value 2 times root t units. And the distance between the planes, the base plane and the top plane is given by subtraction z plus 2 minus z minus 2, z plus 2 minus of z minus 2 equal to 4 units. So there we have a difference. 4 units is the difference between the base and the top of the prism. Clearly the prism is an M set. Okay, and the figure, the geometry of that prism of the equation itself says that the prism can make an M set in R3, in the 3-dimensional Euclidean space. Our prism, the prism that we are discussing, can make an M set. And so M set, you know, the meaning of M set is, I think you know the meaning of the M set. An M set is a non-empty set that is that must be bounded, and that is symmetric about the origin. That must be symmetric about the origin. In general, it must be symmetric about a point. The set must be symmetric about a point. It must be convex, and it must be convex, and it must be symmetric about the origin. And that kind of set is called an M set. Okay, so clearly our prism that is under consideration here is an M set. So we want the volume of that M set. We want to know the volume of the M set. How can we obtain the volume of the M set? You know, there exists a formula for obtaining volume of a prism, especially using using a general formula that is explained there. And for that we need to we will do one separate video for that, for explaining the method of finding the volume. But you know, there exists a formula in which we can substitute the values of the coefficients which are present in the equation that we are considering here, and that values can be substituted in that equation to obtain the volume. There exists a formula for that. See that in that formula we apply, and that formula is also given in the text. In the steps of the proof, it is given there. It is included there in the proof. But here we continue with without giving that the formula. But you know, we will give. Straightforward, we will give the value obtained when the coefficients of the equations are substituted in that formula to obtain the volume. See, the general equation are compared to, so the procedure is explained here for obtaining that volume. General equations are compared to the equations given in 10.3. In 10.3, the values d1, d2, e1, e2, f1, f2, and ab, c1, a1, b1, c1, a1, b1, c1, and a2, b2, c2, then a3, b3, c3, all are then substituted in equation 10.4, and we obtain the volume of the prism. Here our object is prism, and we obtain the volume of the prism equal to 8 units. And therefore you know, you can write, now we are going to represent that volume using the delta, this symbol, using this symbol, this del symbol. You can use this, and del of t equal to 8 units. So this del t, you know, it's equal to, it can be written 2 cube. The volume of the prism equal to 8, that equal to 2 cube. And we can so now what is the importance of writing it as 2 cube? Now we are going to apply a theorem. We are going to apply the Minkowski's fundamental theorem. You can apply if you know that it is the cube of a number, then since it is 2 cube, by applying Minkowski's fundamental theorem, then you can see that n equal to 3 here, since we since we compare it with the 2 raised to n. As we compare it with the 2 raised to n, the quantity 2 cube is compared to 2 raised to n, and we can see that then n equal to 3. Then we get that there exists at least one point, that's a lattice point. Now by applying Minkowski's fundamental theorem, due to that comparison, after comparison we can see that n equal to 3 in Minkowski's fundamental theorem, and then in addition to that, Minkowski's theorem says that there exists at least one lattice point. That point is P1 Q1 R1, P1, Q1, R1, having the coordinates P1, Q1, R1. That point is P1. There is at least one point. We name that point P1 equal to, using the coordinates, it's small P1, Q1, R1. Other than 0, and this point is there exists this point other than 0. That means the coordinates cannot be equal to 0 simultaneously. Okay, and where P1, Q1 and R1 are all integers because it is a lattice point, then integers and okay, and the existence is then where does it exist? It not anywhere. It's very important where the place of its existence is very important. That lattice point exists either inside or on the boundary of the prism. So that's also very important. So there exists a lattice point other than the origin, and that exists either inside the prism. It exists either inside the prism or on the boundary of the prism. So that's the consequence of the application of Minkowski's fundamental theorem here. Since the prism is an M set, okay, is an M set, the mirror image of P1 about the origin is also inside the or on the prism. On the prism means on the boundary of the prism. Okay, so one from the first point we got is that there exists one non-zero point or one lattice point other than the origin inside or on the boundary of the prism. And now by applying or by thinking that when we think that the object under consideration is an M set, it's then symmetrical about the origin. The M set is symmetrical here. It is symmetrical about the origin, about the center point. Here the center point is the origin. As a result, when P1 is a lattice point, then minus of P1 is also a lattice point. The minus P1 here, by minus P1 we mean the geometrically opposite point of the lattice point P1. So it can be written, for convenience it can be written minus of P1, but that has then the coordinates comparing it with the coordinates of the point P1. You can write the coordinates of the geometrically opposite lattice point, that is minus P1 comma minus Q1 or minus Q1 comma minus R1. If it is, it is done minus P1, minus Q1 and minus R1. These are the values multiplied by minus of the first point, first lattice point, the coordinates of the first lattice point. Thus there are two. We can then again restate that there exists 2 points other than the origin, 2 lattice points other than the origin, in or on the boundary of the prism. Okay, and that you can see that situation is illustrated here using the figure. The prism, okay, and a prism has a center at the origin. Okay, it's an M set. The prism is an M set. Okay, and then we take the first point P1 equal to P1 Q1 R1, and its geometrically opposite point can be obtained by joining P1. First we join P1 with the O, and then it is extended further in the opposite direction, and you take that the same distance in the opposite direction. If you measure the same distance between P1 and O, we have a distance, and that distance is measured in the opposite direction to obtain the point that can be called the geometrically opposite point of P1, which is written here using minus P1, or represented here using minus P1, and that has clearly the coordinates minus P1, minus Q1 and minus R1, and thus we have the 2 lattice points. inside, or it can be up to the rare situation. The rare situation can be on the boundary of the prism. Okay. Okay, you can see that it is explained. Figure 10.2 explains the position of the points P1 and minus P1 with respect to the prism, or within the prism, with respect to the center and the position of the prism. Okay, since the third coordinate of the point is R1. See, now we are going to look at the third coordinate specifically, and since the third coordinate of the point is R1, of which point? Of the first point is R1, and that determines the distance of the point from the origin in the Z direction. Okay, and this is very general information. You take any point x, y, z. You take the triplet yes, x, y, z, and the third coordinate is z. It's a number, z. And but what is the significance of that number? You know that that number represents the distance of the point from in the z direction. Distance of that point from the xy plane. Actually, you can say it so. Yeah, from the xy plane, the distance of that point from the xy plane, it's perpendicular distance from the xy plane. In which direction? In the z direction. Okay, origin. But that can be equal to the distance from the origin also. See, it can be parallelly translated to the origin, and that distance can be translated to the origin, and you can then get the distance from the origin. From the origin in the z direction. Okay, we can restate that it is the distance of the point from the origin in the z direction. And the point is inside. See that this is not point point here, and the point is inside or on the prism, and then R1 can take maximum value to. Okay, and then depending upon this information, and we have stated here, that what is that information? It is the information that R, the third value represents the distance, the perpendicular distance of the point in the z direction from the origin. Z direction from the origin. But as we take the origin here, when we take the origin here, and the prism can extend up to 2 units in the upper direction, in straight upwards. From the origin straight upwards, it can go a maximum 2 units, and the prism can extend straight downwards, maximum 2 units. This is the upward and downward extension of that the range of that prism. The prism can range. We can say that, or then you can the prism is here arranged from the maximum 2 units upwards to then 2 units in the downward direction from the origin. So the lattice point, as the lattice point belong to the prism, it can be either inside or on the prism. So it can range, or the the range of finding that lattice point, you can specify that range. You can think about that range of finding that lattice point. Looking or fixing only one direction, the z direction. You cannot. You may not think about the x and y direction. Leaving it for another occasion. We think about the z direction only. The range in the z direction. What is the range in the z direction? Range in the z direction is from +2 to -2. That because the prism has top side or the top face which passes through the point z equal to 2. The top face has the equation. That the top face equation is z equal to 2, and the bottom face equation is this is z equal to 2. Z equal to 2 is the equation of the top face. This is z equal to, and then the bottom face has equation minus z equal to 2 or z equal to -2. When we say minus z equal to 2, that's z equal to -2. So z equal to 2 and z equal to -2 are equations of the top, and this is top and this is then bottom. Okay, in between this top and the bottom faces, only that lattice point can vary. It can, so you can find anywhere in between these two faces. As a result, we can say that in the vertical direction, see, the vertical direction is z direction, or in the z direction. In the z direction, lattice point, wherever you take that lattice point, it can vary from +2 to -2. And also, as the point is a lattice point, its coordinate values are always integers. See again, its coordinate values are, as the point is a lattice point, we are interested in lattice point only. At the moment we are now we are interested in lattice point only for time being, and the lattice points has or coordinates integer values. So see, specifically you can say about the third coordinate. The third coordinate value is r1 here. So the value of r1, that must also be integers. That must also be an integer, not integers. It must be an integer. Specifically, r1 must be an integer. But this integer value, as it can range from +2 to -2. What are the possibilities of this? Of r1 can take an integer value. What are the different values possible to be assigned, to be selected for the third coordinate r1? It is very limited. You can select +2 and you can select -2. Okay, you can select -1. Also you can take a +1, then you can take a 0. So there are thus very limited. Exactly we can say that there exists only 5 values that can be selected for select as value of the third coordinate r1. So those values are +2, -2, +1 and -1, then 0. But as we proceed, our aim is to show that +2 and -2, the values, these are the two values, possible values of the third coordinate r1. But these two values we are going to show that we can eliminate these two values. These two possibilities can easily be eliminated. That is our that is one of our aim of our steps further. Now we are proceeding to show that, or as we proceed we are going to show that we don't want to consider the values +2 and -2. Also we will show that we don't want to consider the value 0. 0 will also be eliminated. That way, that also we are going to show. So after that, how many values will then remain? And then there will remain only plus 1 and minus 1. Only two values, they are plus 1 and minus 1. So how can we then eliminate the possibilities of R getting values plus 2, minus 2 and 0? So this is the discussion we are going to see. Okay. So all this we have finished, we have completed up to this point. Okay, and this figure we discussed. Okay, we discussed about this figure. Okay, then and since the third coordinate of the point is r1, that determines distance of the point from the origin in the z direction. So repetition, it's actually a repetition, but anyway, let's go through the steps for clarity or for and for getting continuity. Okay, in the z direction, and the point is inside or on the prism, r1 can take maximum value 2. So the possible values of r1 are 0, plus 1, minus 1, plus 2 or minus 2. Next we shall show that we can adjust the prism so that r1 takes either 0, plus 1 or minus 1. Okay, that 0, the case of 0, it's actually not eliminated. Here we are going to show that in our steps further. We are going to show that we can adjust the prism. We can adjust the prism means you can adjust the sides of the prism without affecting, without altering, without changing the dimension, means the volume. Without changing the volume of the prism, we are going to make adjustments on the sides, but we don't change the volume. Keeping the volume same, we will adjust the sides so that the new object is also a prism, and also it's an M set. So keeping that property, also keeping the property of the object as an M set, we adjust the sides of the, or the faces of, we can adjust the faces of the prism continuously. You can adjust. Okay, slightly we will adjust the we can again adjust it continuously. You can adjust the faces. So for this, let us imagine that the prism is shrinked. How do we do that? And that is explained here. For adjusting the sides of the prism, we imagine that the prism is shrinked along the z-axis uniformly. See, the prism is shrinked along the z-axis, not along all axes. It is shrinked along z-axis, but if it is shrinked only along z-axis, the volume will be affected. It will change, volume will change. But we want to keep the volume unaffected. We want to continue in all the modified prism. The volume must be same. How much is the volume of that starting prism? The original prism has an volume 8 units. So the volume must be same, means all prisms that we are going to get in our continuous procedure of making changes on the prism, the volume must be same. 8 units, it will continue without any change, the volume. At the second time, and we increase the sorry, there is mistake. At the same time, not at the second time, at the same time, when we shrink the prism along z-axis, we make one more change. We make the change that the same time we increase the other two dimensions. So since one dimension means z direction, in the third dimension is reduced. By shrinking it along z-axis, we are making a change, or we are reducing one of the dimensions. As we reduce one of these dimensions, you have to increase the other two dimensions, otherwise its volume will be affected. So the same time we increase the other two dimensions uniformly, so that the volume of the new prism is 8 itself. Let us denote the new prism by, okay, we are going to get a new prism. At each instant you are going to get a prism, and we will denote that new prism by kh. We will denote the new prism by newly obtained prism by kh, and then del h is equal to, okay, del h equal to, del here stands for the volume, del h equal to del t equal to 8 units. The volume of the first kh, volume of kh equal to volume of kt equal to 8 units. The equations of the 6 sides of the new prism kh are given in the text by these equations are given there in the text, and you can make it by heart easily. Okay, and you can read it and you can make it. So you have to refer page 130 to the equations. That modified equations are given there. Okay, here it is not included, and this adjustment is then made to avoid the possibility of R1 taking volume, the value plus 2 or minus 2. And see, this adjustment is made to avoid. Why do we need this adjustment? We make very purposefully this adjustment. Adjustment means reducing or shrinking along z-axis and simultaneously expanding along the other two axes, x and y axis. And this is made, this adjustment is made to avoid the possibility of R1 taking. We want to avoid, we are trying to avoid the possibility of R1 taking the value either plus 2 or minus 2. We mean we don't want R1 to allow to take plus 2 or minus 2 the values. Okay, thus in the case of the new prism, see, what is the new prism? The new prism is called the kh. In the case of the new prism kh, R1 can take, as we shrink it, maximum level, at maximum possibility for R1 where plus 2 or minus 2. But since we have kh in the shrinked position, or the shrinked prism, since kh is a shrinked prism, then we know that R1 corresponding to, or the lattice point, if there is a lattice point, by applying that theorem, the theorem here also, in the case of all such modified prisms, you can apply the same theorem and get that there exists how many lattice points other than 0? There exists 2 lattice points. First you will get 1 lattice point, and then you can take its geometrically opposite point to get 2 lattice points in total other than the origin. But all these 2 lattice points, there exist clearly, these lattice points exist in kh. Okay, and therefore you can say that R1 in that case, R1 the third coordinate value of the lattice points present in KH cannot take plus 2 or minus 2 values, so they must take plus 1 or minus 1. It can take a value 0 also. Okay, thus the three values. Now for this prism, for the modified prism, the third coordinate values are either 0, 1 or minus 1. For any volume, for every volume of h, for every value of h, not volume, see, because we are talking about h, so it is a real number. As it's a real number, then it has no connection with volume. Okay, it's a real number, it's a value, so it's a value. So for every value of h, when 0 less than h less than 1, when 0 less than h less than 1, then KH contains only finitely many lattice points. And KH, the prism K of h, for every value of h in between 0 and 1, KH can contain only finitely many lattice points. Next, we allow h to tend to 0, or we suppose that h tends to 0. Next, we suppose h tends to 0. Then KH then tends to, as h tends to 0, then KH tends to KT. KH then tends to, KH must tend to K of t, KT. Next, we show that h tends to 0 means that the shrinking effect is disappearing gradually, but it's there. The shrinking is that effect is there. We do not eliminate. We do not eliminate that shrinking effect completely. We don't do that, because in that situation it will be equal to KT. So by as we reduce the value of h, as we allow h to tend to 0, and then we get that the prism, the modified prism, will also then tend to the original prism KT. Next, and also then we know that there exists only finitely many lattice points inside that prism, because it is bounded. Every bounded set, since it is bounded, its boundary is determined by that those equations of its faces, and so there exists only limited number of limited lattice points inside or on the boundary of the prism. Next, we shall show that KT has no lattice points lattice point with R1 equal to 0, and that is the point. I have mentioned that. I have mentioned in my discussion. Early in my discussion, I have mentioned that we are going to eliminate the possibility of R1 equal to 0 also. So finally, after eliminating R1, the possibility that R1 equal to 0, then we will finally end up with the situation that R1 equal to plus 1 or minus 1. So for that, what we have to do for eliminating this the possibility of R1 equal to 0, next we shall show that KT has no lattice point with R1 equal to 0, and this is the lattice point that is the lattice point cannot be in the form P1 Q1, and when R1 equal to 0, there at that part you can substitute 0. So we are going to show that there is no lattice point P1 Q1 0 which belongs to the prism. or inside the prism, this kind of lattice point is not present. P1 Q1 comma 0, P1 comma Q1 comma 0, this lattice point is not there, where P and Q are P1 and Q1 are integers. See, okay, there is a correction. P1 and Q1 are integers. But for the time being, suppose that KT contains a lattice point, then we will get some contradiction. Okay, and if we suppose that KT contains a lattice point of the form P1 Q1 0, and then naturally minus P1 minus Q1 0 will also be there, due to that symmetry, symmetry about the origin of every point inside that M set. This lattice the prism, our prism is an M set, so applying that symmetry, we can say that when P1 Q1 0 is a lattice point, inside it then minus P1 minus Q1 0 will also be a lattice point present in or on the prism. And this point is clearly present in the cross section of the prism and the XY plane. See, when we consider the cross section of the prism, you can see that in this figure, by referring this figure, this is the cross section of the prism. That cross section, the previous picture, you can see I have that was they colored with the blue, and see, this is that blue colored rectangle you can see, or parallelogram, and you see this rectangular parallelogram, this which is drawn blue colored, and that is the cross section of the whole prism cross section of the prism when it is taken using the XY plane, the cross section using the XY plane, considering the XY plane. See, and that cross section is taken, since the lattice point here we are talking about is P1 Q1 0, P1 Q1 0 and P2 Q2 0. The third coordinate value equal to 0 for both these lattice points. Thus, along the Z axis, that point has no displacement. Okay, so, and that lattice point clearly it belongs to the XY plane. Hence, we can say that that these two lattice points are present on the cross section of the XY plane with the prism. Okay. Okay, that's see this figure, this is the cross section separately separately drawn for for clarity, and here this is X axis and that is Y axis, X and Y axis, so because this is cross section, hence you can see that this is present on the XY plane, and so since we can mark the points here, P1 can be as it's a point on the XY plane which belongs to that parallelogram. Here you can see the parallelogram, which is the cross section with the prism. Okay, and so our discussion that we have completed, we have just completed, and according to the discussion, the point P1 must be on this plane, and also it must be, it can go up to the boundary, the point P1. Similarly, it's a geometrically opposite point minus P1, that must be somewhere inside or on the boundary of the prism. Okay, and then in this. Okay, continuing this discussion, we can now think about the equations of the this parallelogram. Equations of the boundary of the parallelogram. And this parallelogram has boundaries parallel two parallel lines as its boundaries. The parallelogram has this parallelogram has its boundaries pairs of parallel lines. See, this parallel line, this line is parallel to this line, and this line is parallel to this line. Now these lines, the equations of these lines can be obtained by substituting. How can we obtain? It can be easily obtained from the set of from the set of equations representing the boundary of the prism. Using the equations of the boundary of the prism, you can easily obtain the equation of the lines. I mean, the line, this is one line, and this is the other line, parallel line, and this is another line, and this is the fourth line. These equations can be obtained. Once again, we want to go back at this moment. We want to go back the equation of the prism. Boundary of the prism. Okay, these are the equations. Plane 1, plane 2, plane 3, plane 4. Okay, and then 5 and 6, planes 5 and 6. In this equation, substitute. These the last two are not relevant actually in this discussion, because and those two stands for planes parallel to xy plane. This is a plane parallel to the xy plane, and both these planes are parallel to the xy plane, so they are not relevant here. But considering the first four equations, when we substitute z equal to 0, because the all the four lines belong to the xy plane. That in the xy plane only x and y are the variables. When we view that, when we think about or when we consider the xy plane as a part of the three-dimensional Euclidean space, then you can see that for every point belonging to the xy plane, the z coordinate value equal to 0. So in order to get this effect, then in this equation you can put z equal to 0. So as in another way we can say that when the point is in the xy plane, and the point is in the xy plane, z value, its z value, as it is it becomes a part of the three-dimensional space, and z value equal to 0. So we can obtain by putting z equal to 0 in all the four equations here, you can obtain a reduced set of equations. From the first equation we get that x plus t minus theta into y minus root t equal to 0, and the second equation is x plus minus t minus theta into y. Then here this term cancels, plus root t equal to 0. So this way you can obtain four equations, and those four equations which are obtained by substituting z equal to 0 in the first four equations here are the equations of the lines representing equations of the lines which are the boundaries, or which make the boundary of the parallelogram in the last figure that we saw. In this figure here, and those equations are written again here. You can just compare. You can see, you can verify whether we are getting by substitution of z equal to 0 in that previously shown set of equations. These four equations represent the sides of the boundaries of the parallelogram. And by combining the equations, or by solving the equations together, these two equations, these two lines make a point of intersection here. See, this line has a point of intersection here with this line, and that line has a point of intersection with this line. This line has a point of intersection with this line, and also here we have a point of intersection. Now, how can we obtain this point of intersection? Identifying in this line and solving it with the other. Take this line, one of this line, and then solving it with the other two lines, but excluding that parallel line. This line is parallel. Which line can be parallel? You have to see that t minus theta, y x plus t minus theta into y. Here we have x plus t minus theta into y. See, this these two are parallel lines because the difference is only in minus root t and plus root t. And when we compare the first and the last equation, see, first and the last equation you can compare, and you can see that the difference is only in the last constant part. So those two are two parallel lines. Similarly, the second and third are two parallel lines. Second line and the third equation, second and third equation represent two parallel lines. So you can suitably then by selecting these lines, and you can solve them to obtain the point of intersection. That's a procedure which you have studied in your lower classes. So I think no further explanation is required for making this point very clear, because it's very ordinary, very simple calculation. For what? Calculating the point of intersection of the two lines. So you can obtain the point of intersections of two lines. You can see that those point of intersections are written here: minus root t is 0, and for this here it is root t is 0. It's minus root t 0 and it is plus root t 0, and you can obtain the coordinates of these 2 points also by solving them and the corresponding equations. The vertex of the vertices of the parallelogram are but they are marked. The vertices of the parallelogram are marked with L bar, M bar. And see the figure: L bar and M bar. Okay, and for that changing for it, these are the quantities for t corresponding to the prism KT. This is the parallelogram, or this is the cross section corresponding to the prism KT. But in a similar way, applying a similar method, you can obtain the cross sections. You can obtain cross sections of the prisms corresponding to KH also. So in that case, we will denote the point of intersections, all the 4 points of intersections, using that number instead of t. We will represent it by h. So MH, LH, M bar H and L bar H will be that cross section, the corresponding cross section in the case of the prism KH. In the case of the prism KH, then the names will also be names of the prism. Names of the parallelogram or the coordinates of the parallelogram will also be named according to that number h, according to the value of h. Okay. Then this and also you can see the coordinates are the calculated values of the points of intersections. The coordinates of the points of intersections are given here, and for convenience it is that intermediate or the middle calculations, simplifications and calculations are avoided here, and that's not given. I mean, the steps for calculating the coordinates of the point of intersection of the lines or the coordinates of the parallelogram are not included here, and but the coordinates of those point of intersections are given because those points are relevant and important in our discussion. and see the values are LT has root T 0, L bar T has values minus root T 0, but MT has values theta by root T and 1 by root T, and M bar T has, but just opposite, it's geometrically opposite, due to symmetry, point symmetry. So we have M bar of T is equal to minus theta. Its sign will then change. So minus theta by root T and minus 1 by root T are the coordinates of these points. Okay. Next, we also then we consider the diagonals of the parallelogram R. See, from the figure it is clear that when we consider the diagonals of the parallelogram, one diagonal is y equal to 0 and the other diagonal is x minus theta y equal to 0. These are the equations of the diagonals. Y equal to 0, yeah, this is y equal to, yeah, y equal to 0, that means x-axis. Okay, and you can see this is the diagonal, this is one diagonal, this red colored line is another diagonal. The diagonals are colored with the red, and this line as it passes, as it is the x-axis itself, its equation is y equal to 0, and but this diagonal can be given after knowing the coordinate values of the points MT and M bar T. You can easily write the equation of that diagonal, that is x minus theta y equal to 0. Now, area of the parallelogram. Next point that we are going to see is the area of the parallelogram. What is the area of the parallelogram? You can see that area equal to 2 units. There exists formula to obtain area of a parallelogram whose coordinates are the coordinates of whose coordinates are given. Coordinates are, the parallelogram has 4 coordinates or 4 vertices, and we also know the coefficients of the vertices, and so using the formula we can obtain that. Using a suitable formula we can obtain that it has the area of the parallelogram is 2 units. The lattice point P1 cannot be present on the diagonal of the. Now, next point that we are focusing at is the lattice point. We have seen that there exists 2 lattice points. First point is P1 and then its opposite point minus P1, and here additionally we have to say that these lattice points cannot exist on the it cannot exist on what? On the no, and these lattice points cannot be present in okay, on that point. Okay, and we can we are going to establish that the point P1 cannot be present on the diagonal of the parallelogram. So by the diagonals are the x-axis first one, and the other one is this line, and these lattice points cannot be present on the diagonal. What happens when it is present on the diagonals? Let's see. For if P1 is present on the diagonal x minus theta y equal to 0. See, if P1, suppose P1 is present on the diagonal x minus theta y equal to 0, then that can imply that. So this implies that situation can imply that. See, P1 has coordinates P1, Q1, right? And then the third one is 0 already. 0. The third coordinate value is 0. But first 2 coordinate values are P1 and Q1. based on our assumption, if since P1 is present on the diagonal, then you can substitute P1 for X and Q1 for Y in the equation of the diagonal, and you can obtain that P1 minus theta Q1, P1 minus theta Q1 equal to 0, which then simply implies that theta equal to P1 by Q1, and it is since when theta equal to P1 by Q1, it becomes a rational number. It says that this quantity P1 by Q1 says that theta is a rational number, but in the statement of the theorem we have accepted that theta we are considering only then it is a contradiction. It's because theta is an irrational number, because let's go back. Okay, have we made any assumption about that value of theta in the statement here? Yeah, theta is an irrational number. See that in the statement itself we have taken theta as an irrational number. So the possibility that theta is a rational number we are not considering that possibility, as we have excluded that possibility, and we get a contradiction at the moment, at the point where we stopped. We are coming back to that point. You can see that there immediately we get a contradiction. Due to what we get that contradiction? And we get the contradiction due to the assumption, due to our thinking that P1 is a point on the diagonal. P1 is a point on the diagonal. The first diagonal we have taken, one of the diagonal is x minus theta y, and if P1 is present on that diagonal, we get that contradiction. On the other hand, suppose it is present on P1 Q1 is present on the other diagonal x equal to, on the x-axis, the second diagonal. We have to exclude both possibilities actually. Suppose it belongs to the second diagonal, and then and you can see that P1 and then become P1 and Q1 are the coordinate values, and then y value becomes 0. As a result, Q1 then Q1 must become 0 when if it is present, if the point P1 is present, if this point, largest point P1 is present on the x-axis, then what happens to the y coordinate? Q1 becomes 0. Thus we get that, and that's a very dangerous situation, because we are very serious about that situation, because we have to come back again to the beginning of our discussion. Okay, beginning of the statement, P and Q where are then integers, where their axis P and Q. Then what happens in this expression? You can see that when Q equal to 0, suppose Q equal to 0, then this quantity disappears here, and then we have then P minus alpha. Then we get that P minus alpha only their axis P minus alpha, but our aim is to show that their axis, we want to find an approximation for we want to find an approximation for the irrational number theta. Actually, our aim of the of this theorem is to find an approximation for an approximate value for the irrational number. And but that point we did not discuss in the starting time of the theorem. the starting point of the of our discussion, we didn't discuss about that, but actually, you know, by proving the Minkowski's theorem, we are trying to approximate the irrational number. So here, see, theta is the irrational number. Theta is an irrational number, and using P and Q, we will find, by using P and Q, we will find a rational number approximation to the irrational number theta. So this is the aim of the theorem. So you know, when we have Q equal to 0, if we take Q equal to 0, you know, when we make the fraction P by Q, it is not possible. You can see that it's not. You cannot proceed further when we consider the fractional P by Q. If suppose Q equal to 0, then you cannot proceed with the number P by Q. So such a situation we are going to face such a situation if we assume that Q equal to 0. So in the last point, at the last point that we were from where we deviated to the first the beginning part of the theorem, you know, here that situation, I mean the presence of the lattice point on the second diagonal on the x-axis must also be rolled out. It's because that leads to Q equal to 0. When the lattice point is on the x-axis, you know, the y-coordinate value equal to 0 also becomes 0. As a result, we cannot take the fraction P by Q. So due to this reason, we just avoid that case also. So that will undermine our the whole purpose of this result. Okay, and that will further be explained. You are going to see in the last part of the proof, the steps of the proof, and before closing the steps of the proof, before crossing the steps of the proof, you are going to see how we will avoid the possibility of Q equal to 0. Okay. Thus we have two cases we have excluded. That means presence of the lattice point on the first or the second diagonal, either the first or the second diagonal. That those two cases were excluded. And since root t is less than 1 by 2, the origin here, since root of t is less than 1 by 2, how do we get this? In the starting part, we have established that root t is always less than 1 by 2. Since root t is less than 1 by 2, the origin is the only lattice point which lies on the diagonal y equal to 0. Okay, and that's also the reason root t. We have a clear reason also here. Since root t is less than 1 by 2. Since root t is less than 1 by 2, see, how can we say that then? The value of root t is then less than 1 by 2. So suppose that the point PQ is on the okay, let's consider this. We can consider the equation. Okay, suppose that the point the point PQ 0 has the value the second coordinate equal to 0. Suppose means Q equal to 0, and this happens when that lattice point is on the x-axis. Yes, when it is on the x-axis. So since it belongs to that point, belongs to since it belongs to the parallelogram, since that point belongs to the parallelogram, when we substitute the you have to refer the figure also. See, when we substitute that quantity in the equation of the lines, that when since the y coordinate equal to 0, since the y value equal to 0, so all these then becomes 0 when we substitute the value in all these equations. Then what happens? Then x plus x, then we get from the first equation, we get that when we substitute the y value, y quantity equal to 0, it then reduces to 0. Then the first equation then reduces to x minus root t equal to 0. X minus root t equal to 0, but x minus root t, it must be so because the point is inside. X minus root t equal to 0. X minus root t equal to 0 happens when it is on the line. On the line, x minus root t equal to 0, x plus root t equal to 0. So or x minus root t equal to 0, x plus root t equal to 0. Thus we get only 2 equations from the 4 equations, or in other words, the 4 equations then reduces to, all the 4 equations reduces to 2 different equations, only 2 equations when we substitute y equal to 0, or when we substitute q equal to 0 in this equation, and it then reduces to 2 equations. What are the 2 equations? X minus root t equal to 0 and x plus root t equal to 0. X minus root t equal to 0. X minus root t equal to 0 means x equal to root t, and x equal to root t, and x equal to minus root t. So these are the 2 values we are going to obtain by substitution of q equal to 0 in the equation of the lines. That means we are going to get the coordinate x. X can vary. Okay, and then we will get then p is equal to then x. The value p equal to x, but by taking that p equal to x, then you will get x equal to plus 2 or plus root 2 or minus root 2. Okay, by solving the reduced equations, we get 2 reduced equations, x equal to plus root 2 and x equal to minus root 2. How do we get that reduced equation? By assuming that q equal to 0. And all these are our current discussion is only based on the assumption that q equal to 0. Q equal to 0, that the second coordinate, assuming that the second coordinate equal to 0, what happens? We are going to see the result of that assumption. So when q equal to 0, the 4 equations reduces to these 4 equations reduces to exactly 2 equations. First equation is x equal to x minus root t equal to 0, that is x equal to plus root t, and the other case is x equal to minus root t. In the x equal to plus root t can give us the value that p equal to 0, because p is the x coordinate value of the lattice point. So when we think about that lattice point pq0, where q is already 0, then we have p 0 0, right? Since q equal to 0, for the thinking only about that lattice point, we can say this. So we have p 0 0. For this p 0 0, if you want to obtain the value of p also in specifically, you get that when we apply it in that equations, you get that x equal to plus root t or x equal to minus root t. I repeat, we get that x equal to plus plus root t or x equal to minus root t. So this leads to the possibility that the first coordinate value, that means p equal to either plus root t or minus root t, p equal to either plus root t or minus root t. Okay, but the value of root t, you know that it is less than 1 by t, 1 by 2, less than 1 by 2. In the beginning, in the first part of the steps of the proof, we were confirmed that we were made sure that and the value of root t is less than 1 by 2, and that says that p cannot be an integer. P cannot be an integer except 0. P cannot be an integer except 0. Since root t is less than 0, since root t is less than 1 by 2, when we take x equal to p, you have to end up with the conclusion that p can take only one value, 0. We will end up with the conclusion that p can take only one value, that is 0. But finally that leads to the conclusion that the lattice point is 0, 0, 0, right? First we have avoided the third coordinate value. We have determined that, we have showed that the third coordinate value is equal to 0. Or we are considering that situation, and then we have taken the situation that when q equal to 0, if q equal to 0, we are discussing about the possibility of the existence of lattice point. Thus we have fixed the third coordinate equal to 0 and second coordinate equal to 0, and after fixing these two coordinates, as we proceed mathematically applying the possible steps and the assumptions, we have finally obtained the fact that the first coordinate will also be equal to 0. So finally we have got a lattice point, and that lattice point is the origin itself. So what is the conclusion of our discussion? All this discussion says that if there exists a lattice point, if there exists a lattice point inside this parallelogram, it cannot be on the diagonal. First when we thought that P1, that existing lattice point P1, if it belongs to the diagonal m bar t, if it belongs to the diagonal m bar t, that means this is the diagonal. If it belongs to this diagonal, we got a contradiction and we get an impossible situation. So then, as the second case, we considered the P1, the situation P1 belongs to the diagonal x-axis. When P1, or we were thinking whether it is possible that P1 belongs to the diagonal, nothing but the x-axis. But if P1, by assuming that P1 belongs to the diagonal x-axis, we have reduced the situation, or we have obtained we have got the situation that the lattice point then must be nothing but the origin itself. And okay, it can belong to, the lattice point can belong to the diagonal x-axis, but then what happens to that lattice point? It becomes the origin. It becomes 0, 0, 0. It must become 0, 0, 0. That means this lattice point cannot exist. It cannot exist along the x-axis as a different lattice point. As a lattice point other than the origin, it cannot exist along the x-axis as a lattice point which is other than the origin. So if it is a lattice point that exists on the x-axis, we must get that we must conclude that it is the origin itself. That lattice point is the origin itself. That is the situation. So, but that lattice point is avoided here, because we know that we were discussing about the lattice point other than the origin. we applying that Minkowski's theorem, applying the previous theorem, we have obtained that, we have established that there exists a lattice point, there exists at least two lattice point which is other than the origin. So we cannot accept this lattice point, which is the lattice point which is that is the lattice point which is obtained by applying that theorem. It cannot be the origin. That lattice point cannot be the origin, so that situation must be avoided. Hence we have to say that the lattice point which is obtained, which is in our hand, the lattice point that is in our hand is cannot exist on in the first diagonal or on the second diagonal. That's all. Okay, then we can complete we can then continue the discussion. Next, continuing the discussion. Okay, so this is the further it is the lengthy discussion on the non-existence of the lattice point on the diagonals. Okay, after completing that the discussion on the non-existence of lattice point on the diagonal, so we get that P1 is a point as shown in figure 10.3. The figure 10.3, yeah, this is the figure 10.3. Here you can see that it is separated. The lattice point is separated. It cannot exist on the diagonals. So while drawing that such a lattice point, care must be given that it cannot, it does not lay on, it does not be present, it cannot be present, it is not present on the diagonals. It does not belong to the diagonals. Okay, that's all. After that, we can easily show that a lattice point cannot be present in or on the parallelogram as shown in figure. Okay, that is the point next we are moving to. Okay, after completing the discussion of non-existence of any lattice point on the diagonals of the parallelogram, next we are moving to show that a lattice point cannot exist in or on the parallelogram. So it is much more serious. Here we are going to show that a lattice point, none of the lattice point no lattice point can exist in anywhere on the parallelogram. Okay, how can we do that? For that, we consider the change in the parallelogram is continuously taking place from T to T1. See, we consider for that to establish that fact. What is that fact that we are going to establish? We are going to establish the fact that no lattice point can exist on the entire parallelogram. It cannot exist. No lattice point can exist. Such a lattice point P1, a lattice point like P1 cannot exist in the in or on the parallelogram. This parallelogram is the cross section of the prism with the xy plane. Okay. Okay, then continue. Let's continue that. Okay, so we consider the changes. Let's consider the changes in the parallelogram as we continuously change the value from T to T1. We have discussed about the value h. What's the importance of the value h? H is the value that decides a small change in the prism, a small change given to the prism, and that change in the prism is obtained by simultaneously shrinking the dimension of the prism along x-axis, but increasing the dimensions of the prism along x and y-axis. So there are four changes. Along x-axis there is a change, its dimension reduces, But along x and y axis there is change. It increases. The change is increasing change. It's increasing. So but this change leads to a new prism. That prism is represented by kh. But this value h can be any number. Continuously you can assign. Suppose the value t equal to 1, then you can represent for a smaller value for 0.9. h can then be used to represent 0.9. h can be used to represent 0.8 also. h can represent 0.7. Likewise, and also if there is change in the opposite direction, then 1.1 can be a number for h, and that way, but when we have two different h values, 0.9 and 0.8, there exists infinitely many values for h, possible values for h between 0.9 and 0.8. Actually we have to consider all those values continuously. So in other words, more clearly, we have to say that we consider all possible real values for h as we make changes in the prism. We make changes in the original prism. We have the starting point. At the starting point we have the original prism, and that prism is subjected to a change by decreasing and increasing its dimensions. Simultaneously we do the both kind of changes. We allow both type of changes, and then we as we consider continuously all real values, and you have to consider the change. When we consider the changes in the parallelogram, then we continuously change from t to t1. See, this t1 is a value for h, so we consider continuous change of h. As we consider the continuous change of h, we have to we have to look at all possible values of all possible real values of h. So that kind of value, one such a value is t1. So see, as we consider the change of t from the value, or as we consider the change of h from the value t to t1, we continuously consider that change. Then the corner points. See, then the corner points empty continuously then moves to empty1. Corner point of the parallelogram. We want to refer that figure. That figure, okay, you can see that figure is given here. We can explain it using that figure. Along with that, simultaneously looking at that figure, we can explain. Okay, but before that, let's see what's explained here. Now we consider the change of h from t to t1 continuously. The corner points empty continuously moves to mt1 along the diagonal x minus theta y equal to 0, and m bar t then changes to m bar t1. M bar t changes to m bar t1 along the diagonal, along the other diagonal. It also changes. See the figure, previous figure here. M bar t changes to m here, but only one parallelogram is shown. So that will be clear when we consider the parallelograms for different values of h. If we consider parallelograms for different values of h simultaneously, then this point will be clear. So for that we refer the next figure. In that figure you can see the original parallelogram that has boundaries, that has its coordinate vertices, coordinate values, or the vertices, vertex points MT, M bar T, LT and L bar T. But we change, as we change the value of H, you can see here we in this direction along x-axis we reduce the dimension, and along y-axis we along the other diagonal we increase the dimension. How do we change that? Change the dimensions of the parallelogram, the cross section, dimensions of the cross section. Here along the x-axis we reduce its uniformly we reduce its dimension, but simultaneously along the other axis, along the other diagonal, is not the axis, along the other diagonal we increase its dimension. But these changes are made following the condition, or keeping in mind that the area is not affected. By affecting these changes, one important point must be satisfied, that the area of the parallelogram continues without any change. So the area of all these parallelograms are 4 units. Area of the parallelogram, 4 of these parallelograms are 4 units. Steadily it is 4 units. Steady it continues equal to 4 units. Okay, then we can then see that the point then M bar T and MT and M bar T, where it changes LT, okay, L bar T or M bar T, it moves along the MT M bar T, it moves along the other diagonal, and but LT L bar T it moves along the x-axis. Okay, the point LT moves to LT1. So you can see LT moves to LT1. It moves to LT1. LT moves to LT1. Then L dash T moves to, or L bar T moves to L bar T1. L bar T moves to L bar T1, and MT moves to MT1. MT moves to MT1, and M bar T moves to M bar T1. But if it further in the same direction, if it is further changed, the value is changed further in the same direction, then you can see that MT1 moves to MT2. So MT moves to MT1, and then it moves to MT2, and then LT changes to LT1, and LT1 moves to LT2. LT1 moves to LT2. Similarly, L bar T1 L bar T moves to L bar T1, and L bar T1 moves to L bar T2. So these are the changes taking place at the coordinates of the parallelogram. Okay, then and we denote this parallelogram by QT. Let's call this parallelogram the original parallelogram by QT, and then the second step parallelogram, which is obtained after the first change, will be denoted by QT1, and the third step it will be denoted by QT2. So we can say that the first step from the point QT, the initial parallelogram QT is changed to QT1, and then it is changed to QT2. So Qt, first Qt is changed to Qt1, and then Qt1 changed to Qt2. See, but one important thing that at this point we want to mention is that this change is continuous. The change from Qt to Qt1 is not discrete, it is continuous. The parallelogram has to pass through all the intermediate positions in order to reach the position Qt1. Similarly, from Qt1 to Qt2, as it changes from Qt1 to Qt2, continuously it goes through the stages of changes from Qt1 to Qt2, or different stages of stages that changes from Qt1 to Qt2. So that is the change, that is the way the parallelogram changes here. And the figure 10.4 shows the changes in the parallelogram as we allow to decrease t to t1. As we allow to decrease t to t1, and further it is allowed to decrease to t2. But 1 by 2, we know that 1 by 2 is greater than root t, we know that, but also we have the relationship t connecting to t1, t2, etc. See, we are actually reducing the value of t. So we know that initially we know that root of t is less than 1 by 2. And also as we reduce the value of t to t1 and to t2, then keep going on to reducing it to 0. We have the relation t greater than t1 greater than t2 greater than 0, and so considering these two relations in the figure, we and also referring the figure, the blue parallelogram is related to, here more explanation is given here. Here you can see the blue parallelogram is related to t, the value of t, and the orange parallelogram is related to t1. Orange parallelogram is related to t1, and the green parallelogram is related to t2, the number t2. So and the blue parallelogram, it is given in different colors in order to differentiate it easily for different values of t. Also note that the orange parallelogram contains p1. Okay, then we want to look at the position of p1 along with the changing parallelogram. Thus we have a situation of changing parallelogram here. And this description, this figure actually depicts a change in the parallelogram. It shows a change in the parallelogram, but we are not able to draw all the parallelogram in one figure. The value of t reduces to t1 and then to t2, then further to another value of t, another different value of t continuously. Actually, we know that fact, but representing the continuous change or related to this continuous change, it is we know that there exists parallelogram. We know that there exists parallelogram corresponding to each value of t as it goes from t to t1, and it reduces to as it reduces from t1 to t2 and further to another value of t. But all these parallelograms, since there exists infinitely many parallelogram, changing parallelogram, these parallelograms are changing, and these parallelograms actually must be drawn on the single on the single figure, on the figure that you can see here. On this figure, all these parallelograms must be drawn, but it is very difficult to draw all the infinitely many parallelograms that undergoes the changes, continuous change. but you have to imagine, but you can keep thinking about this change continuously taking place, the change in the parallelogram continuously taking place, in order to understand the point that we are going to explain further. So, to understand the point we are going to explain, you need to imagine about the changes taking place to this parallelogram. Okay, and then think about, look at the figure, look at this figure, and think about the point. About the point that which point? About the point, the actual point that we have taken as the lattice point inside the first parallelogram, the blue parallelogram. Inside the blue parallelogram, according to our application, as a result of the application of the previous theorem, we have got a lattice point which rests on the and also we are trying to verify whether that lattice point, whether the lattice point belongs to the cross section. We will within few minutes we will see that, we will establish that the existence on the cross section, existence of a lattice point on the cross section is not possible. So we have to remove that situation, we have to remove that assumption that there exists a lattice point on the cross section, but for that we are trying. Okay, but for the time being we assume that the lattice point, there exists the lattice point, but the lattice point P1 on the parallelogram, but this lattice point, this existing lattice point cannot belong to the diagonal, and that possibility we have ruled out. Okay, now suppose this lattice point belong to this parallelogram, and this is, you can see that the position of the, you have to fix that position of the parallelogram excluding the diagonal. Somewhere inside the parallelogram you have to fix the position of the lattice point in the parallelogram. After fixing the lattice point here as at the point P1, after fixing that, you can think about, let's think about the change taking place, change happening to the parallelogram as we reduce the value of t from t to t1, then further to t2, and keep going on that. And what is happening to this parallelogram? This parallelogram changes its size to, its shape to the orange parallelogram, and the orange parallelogram then further changes its shape to the green parallelogram. And likewise it keep going on, but you will get a moment, you will get a particular position of the parallelogram, or you will have a particular value for t. For that value of t, the corresponding parallelogram, for each value of t which is less than t, we have a parallelogram. For each real value of t which is less than t, or for each value of h which is less than t, more correctly, for each value of h which is less than t has a parallelogram associated with it. You have to think about that parallelogram for that particular value of h, for a particular value of h for which the parallelogram touches the lattice point. You see this lattice point P1, then you can see as we draw the changes in the parallelogram, you can see that the parallelogram continuously changes its shape, or its side is continuously moving. Its side is continuously moving, and as it moves further, you can see that it must come closer to the lattice point, and that and orange parallelogram, we have that particular parallelogram. It's drawn here in orange color, and that parallelogram takes that lattice point on its boundary, or it gets that lattice point on its boundary. See, and that is very important. That's an important observation. There exists a particular value of t or h. There exists a particular value of h, and for that value of h, the corresponding parallelogram has the lattice point, our lattice point on its boundary. But you know, as we reduce in the value of h further, as we decrease the value of h further, you can see that the boundary of the parallelogram leaves that point, leaves the lattice point, and it moves away. It leaves that lattice point, or it loses the lattice point from its body. Okay, we can say it that way. Okay, the lattice point thus moves away from. As a result, as we reduce further the value of h, it shrinks. Further it shrinks, and what happens to the lattice point? It then moves away from, lattice point moves away from the body of the parallelogram. See, in the first parallelogram it was inside the body of the parallelogram. In that critical stage, in the case of the orange parallelogram, the lattice point became a point on the boundary of the parallelogram. But as the value further reduces, the lattice point comes outside the parallelogram. Lattice point comes outside the parallelogram, and further it then moves away from the parallelogram. What happens at this situation? At this situation, the green, you can say that the green parallelogram has no lattice point inside or on the boundary. It has no lattice point inside or on the boundary of the green parallelogram. Already we know that the lattice point cannot be the origin. The lattice point that we are especially talking about is not at the origin. We have at least two lattice points other than the origin. So in the situation where we are standing now, we are standing with a parallelogram which does not contain. We are standing with a parallelogram, the green parallelogram. As you can see in the figure, we have a green parallelogram which does not contain any lattice point other than the origin. But you can say that it's an M set. But this parallelogram is an M set, right? It's an M set. This parallelogram is an M set, but and also its area is 4 units. The parallelogram is an M set, and its area is 4 units. Okay, and sorry, its area since it's the other way. Okay, yeah, its area is 2 units. It's not 4 units. The area of the parallelogram is 4 units. Is 2 units because in the upward direction, as we take the when we consider, this is the cross section. You know, it's the cross section of the prism, right? It's the cross section. This parallelogram is the cross section of the prism. But the prism has along the z-axis how many units? 2 plus 2. In the upward direction 2 units, downward direction 2 units. So 2 plus 2 equal to 4 units. So in the z direction it has 4 units in total. So 4 into we know that the volume of the prism is 8 units. So that 8 units is obtained by multiplying 4 by the number 2, right? So this 4 units is the dimension along the z-axis. As we do not have the z-axis here, and we have only the area. So the area will be then 2 units. So that way, geometrically you can say that, easily you can verify that the area of the parallelogram is 2 units. No, this parallelogram is then added with the other dimension, the third dimension. A third dimension is added to this parallelogram in the z direction, in both way, in the upward, in the both way means in the positive direction of z axis and also in the negative direction of the z axis. We add 2 more units, 2 units upwards and 2 units downwards to obtain in order to complete the prism. To obtain the prism, we have to consider 2 units in the z direction, upwards and downwards. Okay, that is then 4 units. 4 into, then how much is the area of the parallelogram? It is 2 units. You know, we are keeping this parallelogram. The changes in the parallelogram is such a way that we are keeping the parallelogram such that its area is constant. Always its area is same. So the area is 2 units for all of these parallelograms. We have the same area, and that is 2 unit. Okay, and that 2 unit is multiplied by the dimension in the, or the length of the prism along the z axis, that is 4 units. So 4 into 2 equal to 8 units. Thus we have 2. We can confirm that area of the parallelogram is 2 units. Earlier I at some point by mistake I mentioned that area of this parallelogram is 4 units. That's a mistake. You must correct that. Area of this parallelogram, it's constant. It's always it's kept equal to the value is kept equal to 2 unit always, without any change. Okay, and then having this parallelogram 2 units, area 2 units, then you have to say that, you can say that, and then there must exist a situation, there cannot exist a situation in which that parallelogram does not contain any lattice point. It does not contain any lattice point other than the origin. See, you can apply the same theorem. You can apply the same theorem here. See, area of the parallelogram, we have the green. We can think about specifically. You have to think. I am drawing your attention to the green parallelogram. See, think about the green parallelogram. This green parallelogram has area 2 units, and it's an M set also. It's an M set. It's an M set and it has area 2 units, and it's of course origin is there inside it. But you know, as we have seen that it can avoid, this green parallelogram can avoid the lattice point inside it. Further you can reduce it. So wherever you take a lattice point inside it, you can see that further reducing the value of t, you will get a new parallelogram which has area the same as that of the previous parallelogram. The previous, its area is same, so same, and it is equal to 2 units, but it can avoid that lattice point that you have thought as existed in the previous case of the parallelogram. So what happens, you will get a parallelogram, its area is equal to 2 unit, which is convex, which is an M set. So it's an M set, and its area is equal to 2 units, but it contains no lattice point other than the origin. So it's a dangerous situation. It's a contradiction. It's a contradictory situation. So what we get that there does not exist then a okay, and so there does not exist our assumption that there exists a lattice point. There exists a lattice point inside the parallelogram is thus wrong. Okay. then so see, this is then considering it is then 2 unit. Okay, its area is here it is mentioned, its area is 2 units. Now considering the prism, then see, we are then taking the prism, we are going back to the case of the prism, considering to this, considering to the green, considering to all of these parallelograms. We take our attention to the prism which exists corresponding to the parallelogram, the green, the blue, the orange, and the green parallelogram. So when we think about that prism, okay, consider the prisms corresponding to the green parallelogram. Specifically, if we think about that green parallelogram, in this prism, and there is no lattice point, you can see that there exists no lattice point, and still it's because we know that that green the green prism, sorry, the green parallelogram can avoid the lattice point, that which we assume to exist, in the initially in the blue parallelogram. Initially we assume that there exists we assume that there exists a lattice point in the blue parallelogram, but further reducing the parallelogram to the orange parallelogram, and then further when it is reduced to the green parallelogram, the green parallelogram avoids the lattice point. So the lattice point, this is the lattice point we have mentioned that exists. This is the lattice point that we have mentioned that exists in the prism. Actually, that exists in the prism, and we are trying to show that lattice point cannot exist in the cross section region. Okay, if it exists in the cross section, then that resizing of the parallelogram can avoid that existing lattice point. Further, when we consider the whole prism corresponding to that avoiding that corresponding to the parallelogram that is avoiding or that can avoid the lattice point. See, this is the parallelogram that can avoid this lattice point. The parallelogram, green parallelogram, can avoid that lattice point. So then, corresponding to this to this prism, if we take the corresponding to this parallelogram, if we take the prism, then we can say that prism also can avoid that lattice point, which we assumed initially. We assumed that exists, not assumed, which we established, that which we clearly we got that by applying the theorem. We have established that there exists. We have got that there exists one at least two lattice points. There exists two lattice points which belong to that prism. But we have now by taking corresponding to the green parallelogram, when we take the prism, we get a prism. Its volume is equal to 8 units. Having the volume equal to 8 units, but unfortunately that avoids all the lattice points. What we get then we get a contradiction to the theorem. We get a contradiction to the theorem that if there exists an M set whose area, whose dimension is 2 cube. If there exists an M set whose dimension is 2 cube, then it must contain how many lattice point? Yeah, here it is explained. So consider the prism, and then that has area, that has, again mistake, that has a volume 8 units. See, still the volume of that prism is 8 units, and then we have an M set having volume 2 cube in R3. Actually, it is in R3 in the 3-dimensional Euclidean space. Its volume is equal to 2 cube. Then which does not contain. Then we get that prism does not contain any lattice point other than the origin. So see, that is the situation we have established. That situation the situation we have established, and that avoids that lattice point, which we initially obtained that exists in the prism, but now we have avoided that. We have created a situation in which that prism avoids that lattice point. Hence, the result the theorem, the meaning of the theorem is now is contradicted. So the Minkowski's theorem is contradicted for n dimensions, and this is the theorem which is contradicted is the Minkowski's theorem for n dimension is contradicted here. So we have to, at the moment, at this moment we have to say that lattice point does not belong to. So why this problem happened? This problem has happened because we have assumed that lattice point which exists in the M set, which exists in the M set, belong to the cross section, and that is the problem. So this point we will correct. So it does not belong to that cross section of the M set, cross section of the parallelogram with the XY plane. So it can be present somewhere else inside the prism. It can be present somewhere else inside the prism, but not in the cross section. Okay. Now for t root t is less than, since root t is less than 1/2, then we have two cases. Okay. So at the point, making this point where we are now standing in the development, while developing the proof of the theorem, we are standing at the point that in the prism we have lattice points. Applying the Minkowski's theorem for n dimension, applying that theorem, we know that there exist lattice points other than the origin, but that lattice point cannot be present where it cannot be present in the cross section of the prism with the XY plane. Okay, and that means it cannot be present. The cross section means Z value cannot be equal to 0. That's all. So when it cannot belong to, when the lattice point cannot belong to the cross section, we have to say that there is a, see, if it belongs to the cross section, then Z value it has no change in the Z direction. So Z value is strictly 0. So if it does not belong to the cross section, then Z value is an integer but not equal to 0. Z value of the point of which point Z value of the lattice point is not equal to 0 but some integer other than 0. Hence we have to say that we have to say that z value of the lattice point is either +1 or -1. I think you remember that the point where we mentioned that we are trying to avoid the situation +2, -2 and 0. The situation for the z value to become +2 and -2, and those two situations initially we avoided, and the situation that the z value of the lattice point becoming equal to 0, that situation has now it has also been eliminated. And thus we have in concluding the discussion so far, we can say that the lattice point has z coordinate value equal to +1 or -1. Next, for root t less than 1/2, by considering the value of root t less than 1/2, we have to consider. We have to take two situations. Situation 1, or case 1, the prism kt. Think about the prism kt. It has the lattice point having the form pq plus 1. The lattice point having the form pq plus 1. And the second situation is the prism kt does not have a lattice point having the form pq plus 1. See, if it does not have a lattice point of the form pq plus 1, then what happened? That situation, in this situation, cannot happen. So it must have a lattice point of the form pq plus 1. Now it is clear from the discussion so far, it is now clear that the lattice point, all the lattice point have the form, if there exists any lattice point, it has the form pq plus 1. And suppose it does not have the form pq plus 1. So in this situation, this is the situation. Then 2, all lattice point. Okay, then the point kt does not have a lattice point having the form pq plus 1. Just imagine if it happens. Then further going, and 2, all the lattice point of it are of the form. So suppose all the lattice point are of the form pq0. So this situation was this situation has been eliminated. From due to our discussion, we have discussed that situation, eliminating that the dangers of the situation we have discussed. So this case is eliminated. It's now eliminated, and these points are then present in the corresponding parallelogram. Qt, and then by reducing the size from once it's a repetition actually, by reducing the value of t to t2, from t to t2, first from t to t1, and from there from t1 to t2 it can further be reduces from t1 to t2. Then we get a parallelogram qt2 qt1. Between qt1 we get from qt to qt1, from qt1 to qt2 with qt2, and that qt2 does not contain any lattice point. And when we take the corresponding parallelogram kt2, that must contain a lattice point having the form pq1. So that must then contain a lattice point having the form pq1. Okay, so all this discussion together says that any lattice point belonging to the prism must be of the form pq plus 1. Then it will have a pq minus 1 also. So then for this value of t, now establishing this, once this is established, so this is finalized, that is, there exists a lattice point pq plus 1. This is the point we actually wanted to show. Thus we have showed that there exists in the prism there exists a lattice point having the form pq plus 1. After that, now we come to our equation, set of equations. So for this value of for that value, that value of t for which it exists, for that value of t there exists a lattice point of the form pq1 pq plus 1 in the prism, then we can we can substitute in the equation, which equation, one of the equations we take and we can substitute. The equation that we take is, see, in that one, p then q y x minus theta y. Okay, go back to, let's go back to the set of equations. Okay, yeah, here if you take that modulus, along with that modulus you can take, okay, in this equation, either this equation or one of these equations is taken, and there you can then substitute, in this equation you can substitute, but since this belongs to the boundary, when we substitute an inner point, we know that the lattice point corresponds to either, most of the case it belongs to the inner point, but in very rare situation, in very rare situation that that point can belong to, the lattice point can belong to the boundary also. When it belongs to the boundary, then you have that value equal to exact that equation you will get. You get a balanced equation. Otherwise, if it belongs to, if the lattice point belongs to the inner part or the interior of, if it belongs to the interior of the prism, if it belongs to the interior of the prism, then you have to write the inequality. You have to write the less than inequality when we use the equation. That's all. So we take this equation. Inside in this equation you have to substitute, you have to replace the value x equal to p because the lattice point is p comma q comma 1. And so you can replace x by p and y by q and z by 1 you can replace, and then this y also you can replace by p, and then you can see that this the equality then must change to inequality. So in all situation, always you can write it as less than or equal to. So that is the equation which we obtained there. This is the point where we the point that we last discussed. We are coming back to that point that we last discussed. Here you can see that since this point x is okay. Yeah, in that equation you can take that equation. In that equation you can substitute. See, this is equal to t, then it is, you can write it less than or equal to t. In that equation you substitute x, you can replace x equal to replace x by p and y by q and z by 1, and then you can see that modulus of p minus theta q minus then alpha, since z equal to 1, you get minus alpha plus t into modulus of q, y becomes q, and is less than root t. It is then less than root t. But if it does not, okay, that does not clearly belong to the boundary. Yeah, it does not belong to the boundary because that situation you can avoid by yes, it's because that boundary can be that situation when and the where it is on the boundary, because but when it is when that point belongs to the boundary, you get equality. But you know, when that point PQ if X and if P and Q belongs to the boundary, okay, then we have for various values of t, you know, even if it belongs to that lattice point belongs to the boundary for a particular value of t, then you can take some other value for which it belongs to the inner portion. Okay. Okay, that's why we take here the less than inequality, and then the point will be inside the point will be inside the prism. Okay, the reason it's explained here. Okay, for this value of t, you can see that yeah, this is the situation. We need to explain this situation a little more. See, you can see that there must contain at least one lattice point having the form PQ1. So for this value of t, for that value of t for which it belongs to, for the lattice point PQ1 belongs to the lattice point belongs to that prism, and for that value of t we have then when we substitute it in that equation, the previous equation, then we get the inequality which is given here, you know, by replacing x and y. Okay, and the reason is given here, and since PQ1 is a point, it is well inside the prism. This point is well inside the prism, and whose boundaries are determined by modulus of x minus theta y minus alpha z plus t into modulus of y. Modulus of x minus theta y minus alpha z plus t into modulus of y equal to root t, and when we substitute then we substitute x equal to p, y equal to q, and z equal to 1, and then we get this one, this inequality. You know, by varying the value of t, you get that situation that it is inside that point is well inside the, you get a prism yeah, which contains that the lattice point well inside it. Okay, and so for that prism you have the inequality less than the inequality less than as given here, that's modulus of p minus theta q minus alpha plus t into root plus t into modulus of q is less than root t. We know that root of modulus of a into modulus of, but this is this inequality, you can see an inequality, root of modulus of a into modulus of b less than or equal to half of modulus of a plus modulus of b, half of modulus of a plus modulus of b. We have that result. This result is separately proved, and not for it is taken from it's a standard result proved somewhere else, and we accept this result, root of modulus of a into modulus of b less than or equal to half of modulus of a plus modulus of b, and then taking here at the place of modulus of a, see, we put modulus of a equal to, we assume that modulus of a equal to modulus of p minus p minus theta q minus alpha, modulus of p minus theta q minus alpha, and modulus of b is equal to t into modulus of q. We assume that because t is already taken positive, it's assumed that it's a parameter, positive parameter, and less than such that root t is less than 1 by 2. it's the choice of t. From the choice of t, it's positive. So modulus of b is equal to t into modulus of q. We set that, and then using this inequality, you get that when we substitute the these assumed quantities, then we get that root of t into modulus of q into modulus of p minus theta q minus alpha is less than or equal to, for the price of modulus of a and modulus of b, the values are substituted and it is divided by 2, and then you get that this is less than this quantity is less than root t y is then squaring, it's less than root t, because of this inequality we know that this is when we consider this quantity it is less than root t because of this inequality. Here we have that this quantity, left hand side quantity, is less than root t. So that left hand side quantity, you have that left hand side quantity here in the numerator, so that numerator is less than root t. So when after replacing that by root t, we get that it is root t by t by 2, root t by 2, root of t by 2, and then we can rewrite that this is less than root, left hand side is less than root of t by 2. Now next we square both sides. The next step is taking square on both sides. Then we get that we get here square root removed, and from the left hand side, in the left hand side square root is removed, right hand side we get 1 by 4. So modulus of q into modulus of p minus theta q minus alpha is less than or equal to 1 by 4. Also since modulus of p minus theta q minus alpha plus t into modulus of q is less than root t, right? Less than root t, and t into modulus of q is positive. Since t into modulus of q is positive, we can remove it again. We can remove it from this equation, from this inequality here. The same inequality we use, and we refer this inequality since this quantity t into modulus of q is positive. So if this quantity is removed, we get that this inequality is further be it will continue, this inequality continue without any affecting the inequality. It can continue even if we remove this this positive quantity. So we get that modulus of p minus theta q minus alpha is less than root t. Okay, by removing this quantity from that inequality, we get that it is less than root t. And but you know, root t is less than minimum value of epsilon alpha minus alpha in square bracket and 1 minus alpha plus alpha in square bracket. So we have so since root t is less than minimum value of this quantity, so if you can directly compare root t with the epsilon, thus we get that modulus of p minus theta q minus alpha is less than, see here we have root t, but that root t is less than epsilon, so we get this inequality, root t less than epsilon. And since we can since we can take epsilon arbitrarily small, very small, since we can take epsilon arbitrarily small, then modulus of p minus theta q minus alpha is greater than 0. And also we know that this is positive quantity, so it is greater than 0. Modulus of p minus theta q minus alpha is greater than 0. See, we refer this epsilon can be allowed to move to 0. It can tend to, we can allow epsilon tend to 0, epsilon to tend to 0, and therefore we get that so modulus of p minus theta q minus alpha is greater than 0. Hence there exists infinitely So we get that there exist infinitely many integers p and q satisfying the expression 10.j and 10 dot j and 10 dot k. See the expression 10 dot j is this one less than or equal to 1 by 4. 10 dot j and 10 dot k is equal to modulus of p minus theta q minus alpha is less than root t. And these are the two expressions, two inequalities that we actually we wanted to prove to establish the theorem. Okay, we have obtained that, and then finally we get that there exists infinitely many integers p and q. Actually there exists infinitely many integers. There exists infinitely many integers p and q satisfying the expression 10j and 10k. Why? Because epsilon is a quantity that can be allowed to move to 0, that can be allowed to tend to 0, and for each of these infinitely many values, there can exist corresponding to each of the infinitely many values, there can exist values for p and q satisfying the above inequalities, which are given in 10 dot j and 10 dot k. Next we shall show that q cannot be equal to 0. Okay, this is the point where, and actually this discussion was completed in our flow, in the normal flow of the steps of the proof. We have completed it, but further some formal way of showing that q is not equal to 0 also exists. We can see that we can show that q cannot be equal to 0. See what happens if q equal to 0. If q equal to 0, refer 10 dot g, the refer the equation 10 dot g, that gives us the 10 dot g is where is 10, referring 10 dot g. This 10 dot g okay, 10 dot g is modulus of p minus theta q minus alpha plus t into modulus of q is less than root t. Okay, and that is now suppose what happens to this expression when q equal to 0, and when we put q equal to 0, it reduces to modulus of p minus alpha plus t into, and that also becomes 0. So p minus alpha is less than root t. We get that situation when q equal to 0. Assuming that q equal to 0, we get that modulus of p minus alpha is less than root t. And let's come back. Okay, and then that is the situation. Here it is given, and since alpha is not an integer, see, alpha is not an integer. Since alpha is not an integer, but p must be an integer. But alpha is not an integer, and p cannot be. So since p is an integer, p cannot be closer to but t, the value of t must be less than, t is less than 1 by 2. Actually root t, we have that relation. We have the value, a condition on the value of t, referring that, you can say that since alpha is not an integer and p is an integer, p cannot be closer to alpha, and then either we have alpha in square bracket or alpha in square bracket plus 1, then either okay, then sorry, it must be closer to alpha than either alpha in square bracket, and these are two integers, alpha in square bracket or alpha in square bracket plus 1. Since alpha is not an integer, and but p is an integer, so p cannot be closer to alpha than either in a alpha in square bracket or alpha in square bracket plus 1. So modulus of p minus alpha must be greater than or equal to alpha minus alpha in square bracket, or modulus of p minus alpha must be greater than or equal to alpha plus 1 minus alpha, alpha in square bracket plus 1 minus alpha. But by our assumption, in both case, by our assumption, root t, and this is the relation, value for root t is less than minimum value of epsilon alpha minus alpha square bracket, alpha plus alpha in square bracket plus 1 minus alpha, and this is actually this is then contradicted, and this value of root t, actually this is an important condition we have accepted on root t, on the value of root t. This value will be then contradicted by any one of these situations. Here we have either this situation or the other situation, the second situation, and that these two both of these situations, whatever the situation actually actually there exists, in both situations, whatever is the case, we get a contradiction. Both case we get a contradiction to our fact that root t is less than, the value of root t is less than minimum value of these three quantities, and thus not avoid the contradiction. To avoid this contradiction, we have to accept that q is not equal to 0. Q cannot be equal to 0, and that is the correction on the value of q, or that is the value, that's the exact value of q. I mean q cannot be equal to 0, and hence we get the complete part of the proof. Actually the part that q cannot be 0, it was actually explained in our earlier in our steps that we proved almost at the middle of the steps of the proof. Okay, then completing this, we can stop here. Okay, thank you.